Hey, welcome to the Art of Code. My name is Martijn, and what you see behind me here sadly is not my bathroom, but I put that there to kind of talk about different tilings that you can have. So I think we can all agree you can tile the plane or your bathroom wall with squares. You can also tile it perhaps with hexagons, and maybe even if you feel fancy you could tile it with triangles. But my question to you is, can you tile it with pentagons? And if you said no, then you're wrong, because you can. And not only in the ugly way, the ugly cheaty way that you see over here, but in a much more harmonic way, much more beautiful way, harmonious I should say, way, namely like this. And this is called the Cairo tiling. And I think it's an absolutely beautiful pattern. It looks a bit organic in a way, yet it's still geometric at the same time. And it's not nearly used enough, in my opinion. So it was kind of hard to find these. And I don't know why. Why aren't there Cairo tiles all over the place? Because they're absolutely beautiful. I mean, look at that. And also they've been invented, kind of semi-invented a while ago. Here is an Islamic piece of architecture. On the top left there we see hexagonal tiles. Down here we see something that is almost, it's just missing one line here. That's almost a Cairo tile. And here was another one that I found that actually is the Cairo tiling. Yeah, which is really quite an interesting, beautiful pattern. It's also used apparently for some cool marketing shots here for this amazing pen. Now, I thought that this is a really cool pattern that isn't used very often, that isn't constructed very often, so I thought I would make that in this video. So if that interests you, then stick around. So here we have the Cairo tiling that we're going to try to make. Make sure you have your big mug of tea and make sure that you have something to eat. I have a beautiful Dutch stroopwafel, which I can really recommend to people with a Cairo. Oh no, hang on, it's only a square tiling. Oh well, then I guess we're gonna have to make our own one. So yeah, so here you see the pattern, and if you look at it for a while, then or maybe you see it right away, like the first thing that you could notice is that this is an overlap of two hexagonal tilings, namely the red one and the green one. Now that is how a lot of people that look at this at first see this, and I looked at some ways of constructing this tiling, and all of them are kind of complicated, I find. And then I saw, I noticed that this is actually, there's a simpler pattern going on here. It's not two hexagonal patterns. It's actually just a bunch of very simple shapes that are stuck inside of a square pattern like this. So so we have just this pattern, and then for every other tile that pattern is flipped around, like so, right? So we have that one and we have that one, which are basically the same, they're just flipped around. And then the other thing to note is that like this very basic shape is also it's very symmetric, right? Symmetric left to right, symmetric top to bottom. So that's great. So we can leverage a lot of symmetries in this pattern. So so let's try to build this. So if you're new to my channel, then maybe you don't know that I do most of my stuff inside of this website called ShaderToy. It's a website where you can do shader coding, which is like make cool little graphic effects directly in the browser and you don't need to install anything, and it works right away. Now, if you're new to shader coding, I recommend starting at a different video. I will put the link in the description, ShaderToy for absolute beginners. There's a few things that I might skip over, like in order to make it a little bit faster, and yeah, not get stuck on small details. Even though I do explain everything exactly about the Cairo tiling in this one. So anyways, so I went to ShaderToy here, and I'm gonna click New to create a new shader. Let's start coding this thing. So the first thing I'm gonna do is I'm just going to get rid of some stuff here. I'm going to make it that my UV coordinates, which indicate which pixel on the screen I'm rendering currently, have their origin in the middle. So I'm going to do that by doing this. I'm going to just subtract half the resolution from the frag chord, which is in pixel coordinates. I'm going to subtract half the resolution, and then I will divide it only by the y, and that will make it that the origin is in the middle, and we are aspect ratio corrected, so nothing is stretched. All right, so that's that. So now we're going to make a black screen. So a black screen would just be a 0 for the red, green, and the blue, and that's our starting position. Let me just empty my mug here. All right. Now the first thing I'm going to do is so that basic shape has symmetry, right? It's symmetrical left, right, and top to bottom. And so I'm going to make use of that. So I'm going to make a vector 2, call it P, and I'm going to take my UV. I'm going to take the absolute value of that, and then let's first just draw out a little square. And one way to do that is I can say if p.x is larger than 0.5, let's say, then my red, I'm going to add something to it, so that I'm going to get a red. And I'm going to get red on the left side and on the right side because I have this absolute here. So for the price of 1, I get 2 borders. And I could do the same thing with the y, right? So I could do that with the y as well. It's just that I can't see it right now. I have to zoom out a tiny little bit. So to zoom out, I can just do that. And you can see on the top and on the bottom, I have that as well. And so I'm going to combine those with a max function. And that's going to combine both left, right, and top and bottom. All right, so now inside of this, I'm going to make that basic shape. And what I'm going to do first is I'm going to so because it is symmetrical, left, right, and top and bottom, I only have to really worry about one quadrant of this, right? And inside of this quadrant, I only have 2 lines. I only have a line that comes like over here, and then the line that goes down. So let's make the slanted line that comes through the corner there. Yeah, so in order to make a slanted line, I'm going to calculate a distance to that line. And in order to do that, I can use a dot product with the position I'm at, and then some normal, which indicates how the line is oriented. And that normal is just a around the clock vector, basically, of length 1. And so for that, I can use a sine of an angle and a cosine of an angle. And then I need an angle. And for the angle, well, go over here, the angle equals, for now, I could just say, well, take the y position of the mouse, and then, because these are trig functions, and then multiply that by pi, let's say, just so that we have like a half the phase of this entire wave. And so mouse, I don't have a mouse, so let's make mouse. So I'm going to say vec2 mouse equals iMouse.xy divided by iResolution.xy. So this just makes the mouse position when my mouse is in the lower left corner, that's going to be 0, 0, 0. At the top right, it's going to be 1, 1. Okay, so now let's visualize that. So I'm calculating a distance here, right? So let's just visualize the distance. So I could just do that, and I can see what's going on. And now if I move my mouse, some weird things are happening. And it's perhaps a bit hard to see exactly what's going on. So let's just turn off the symmetry for 1 second. So go over here. And now you can see that we have a gradient that we can rotate around here. We can rotate it exactly 180 degrees, which is this pi radians over here. So now I don't want a gradient, I want a line. And in order to have a line, let's first make it that the black part of it, which is where the distance is negative, right, this is a signed distance, meaning it can be positive or negative based on which side of the line you're on. But I don't want a signed distance because I want, on the other side, I don't want it to be negative, I want it to be positive as well. So for that I can just take the absolute value. So now I have positive on both sides, and now I want to cut out a sharp line. And for that I can just use a smooth step. So I can go smooth step, and then if you want to get fancy, you can do F with D and 0. And let's see what that looks like. So that gives me theoretically a 1 pixel line, and then I can subtract something small from that to get a nice anti-alias line. Now F width, sometimes sometimes it gives you utter trouble. So I'm not saying to always use it, but you know, you can play with it to get something that is anti-aliased very nicely. But this could also just be a very small number as well. So you could just do that. Yeah, anyways. So let's make it a little bit thinner. And here as well. Well, yeah, let's get back to the F width. Okay. All right, so now I have this line, but this line is rotating around the origin right now. This was the origin of my box. And I don't want it to rotate around the origin. I want it to rotate around the corner over here. And to do that, I can just remap. Basically, what I have to do is I have to remap the origin so that the origin is now over here, right? And what is this position? Well, this is 0.5, 0.5, because that's where the edge of our box is over here. So if I subtract from this, right, so let's say 0.2, now I'm kind of like there, and if I subtract all the way 0.5 from it, now I'm at the corner there. All right, so now let's turn our mirror back on to see where we're at. Okay, so now we have this. So that's already almost what we need. We just need one line in the middle here. And for that, so this is our slanted line over here. Let's just write that down, slanted line. So now we need a straight line, right? So, and because this is just a distance that I'm calculating here, I can use the distance field operators to put things together the same way as you would do if you're familiar with ray marching, the same way as you would do in a ray marching shader. So I can get the straight line. So the straight line would just be p dot x basically, right? Because p dot x is negative over here, it's 0, and then it goes to positive, and then this absolute makes that folds the negative part onto the positive, and then you get that. So I have to just merge those two together. So I have to do d and then p dot x, and now I have both of them. That's awesome. Now over here I don't have that, so over here I can do, well, at first I thought I could just do the same thing, p dot y, but it turns out it gives me the wrong line, and that just has to do with the fact that these are signed distances. They have a positive side and a negative side, and so in order to get around that, you just have to jiggle around with this a little bit. So the way that I fixed it is I made this into a max and then made this negative, and then it gives me this stuff in the middle. All right, so that's basically our basic shape. Now let's make sure that it can't do this, right? Because we're only interested from really like the only shape that the original Cairo tiling had was like about this, right? But we can play with this. So I think it's interesting from here to here. So let's do that. So this is from, my mouse is at 0.5 all the way to 1. So let's remap that. So let me just call this over here. Let me call this K. And then I say float K equals mouse. So that didn't change anything. But this goes from 0 to 1, right? So this goes from 0 to 1. But I need it to go from 0.5 to 1. So, well, that's simple enough because, okay, K goes from 0 to 1. So if I multiply that by 0.5, now it goes from 0 to 0.5. And now I add 0.5 to it. And now I'm from 0.5 to 1. Okay. And so now it goes nicely like that. All right, well, that's pretty cool. So now let's see what this looks like if we make a bunch of these boxes, right? So the way to do that is first I'm going to zoom out a bunch. Okay, and now, so now my UVs go from whatever, -4 to 0 all the way to 4. Well, now I can make that into separate boxes by using a fract function. So fract just makes it that just throws out the integer component of your coordinates, so that, you know, 2.1 turns into 0.1 and 3.8 turns into 0.8. And so it basically makes it like that it repeats everything. So I can do that, but now I have to make sure that my origin is in the middle of each box, so I have to subtract 0.5 from it. And now my box has disappeared, and that's because my box is, or the red part only starts after 0.5, and my box is exactly 0.5. Well, it goes up to exactly 0.5, so if I want to see it, I just have to make this a little bit smaller. And now I can see all my boxes. That is pretty neat. So this alone is already a pretty cool pattern, actually. If you look at this, let's have a look at this. Let's enjoy part of our stroopwafel. Well, I guess if you want to make a chain link fence or something, then that could be pretty cool. Wow, this kind of looks like it could be a chain link fence. So yeah, so that's what I do a lot when you're shader programming and you're doing all these things, and you know, you're slowly figuring out what's possible, right? This is kind of a cool tiling. This is a hexagon with a, what is this, a trapezium or something, or a rhombus. So yeah. So that's a different kind of tiling that maybe could be employed at some point. But that's not what we're doing right now. We are making a Cairo tiling. So for the Cairo tiling, we have to flip every other tile around. And whenever you want to flip every other thing on a square grid, you have to think about a checkerboard, right? So let's make a checkerboard. And in order to make a checkerboard, first I need to know which cell I'm in. So I'm going to give an ID to each cell. And the ID is like 0, 0, 1, 0, 2, 0. And if you go up, it's 0, 0, 0, 1, 0, 2, stuff like that. And I can just do that like that. I can take the floor. And now I can make a checkerboard by adding the id.x and id.y and doing that modulo 2. So that's basically divide by 2, see what the remainder is. And so the remainder could either be 1 or it could be 0. We can visualize that. So I can say call plus equals check. And then you can see that now we have a checkerboard. Oh. And so now, obviously I'm not going to add that color like this. But what we could do, let me just, let me do that over here. What we could do is we could say if check equals 1, then flip it around. So how do you flip it around? Well, basically the x and the y coordinate need to be flipped, and I can use a swizzle for that. I can just say p equals p.yx. So p is basically shorthand for p.xy, right? So that's how you can flip them around. And would you look at that? Let me just turn this off. Wow, Isn't that beautiful? It's a Cairo tiling. Oh. And what's more, and the bathrooms didn't have this, is that we can play around with it. We can change it. See, this is an issue you get with F-width. So that's the reason why I don't always like to use it. So let me just take that out, 0.01, because then we don't have that issue. All right, so that is pretty cool. It's pretty cool for an outline, but let's see what else we can get. Because when you have a pattern like this and you want to use this for as an ingredient to whatever the rest of your shader or your visual effect or whatever, you want to figure out what other information you can get, right? So basically the information that I would want, I don't want just the outlines. I would want to know for every pixel on the screen, I would want to know what is the closest edge and how far away is it, basically. Basically, how far away is it? I want that distance field to this entire thing. And we kind of have that. Let's visualize it. So that's this D, right? The D is the distance. So let's do col plus equals D. And let's have a look. And so, yeah, it's like, it looks good over here, but over here, you can see that there is a disconnect here, right? Like this extra part is not taken into account. And that is because if we take one of these squares here, and we take like a pixel inside of the square, let's say where my cursor is, we are only considering the slanted line, this line, and the straight line, that line, and then a second straight line, which is the other one, right? So the one straight line is this one, the other one is that one. But what we're not considering is the other line that's outside. So let me see here. Yeah, so over here, so for this pixel we're considering this line, we're considering that line, but we're not considering that line because that line is in the adjacent tile, but we do need to consider that. So let's add that line. So yeah, these are the straight lines, right? So straight line and straight line. Okay, but we also need to consider the neighboring line, right? So for that, so the neighboring line, so one thing to realize here is that, let's say if we're looking at this one, so this is the slanted line. Well, the neighboring line is always at a 90-degree angle from the slanted line, and that is kind of handy. So that means that we don't have to do a whole bunch of recalculation, which is kind of great, because we can just use the same thing as we did for the slanted line, so this one, except the N, which gave the direction of the line, is 90 degrees rotated. And how do you rotate something 90 degrees? Well, you just swap the X and the Y. So you have n dot y, n dot x, and then you negate one of them. And I'm going to negate this one. Let's see what that does. So yeah, before I compile it, you see that there is a disconnect here, and now when I recompile it, that disconnect is gone. That's awesome. So it's gone over here. It's yeah, okay. Well, this works perfectly. All right, so that's one thing. That's stroopwafel time. So the next thing that I would like to know is we would like to know which cell we are in, or at least we want to know when we're in one cell, we want to know that we're not in a different cell, because maybe what we want to do is well, we want to have individual control over the cell, so that maybe one cell is bright, another cell is not bright, right? And so we need an ID for that. And so let's see what we can do for that. Let me just get the grid lines back. So now one question is, like, how can we lay out this ID? And the way that I came up with is that we can just take the ID of the square, which we already have, right? Let's say, well, every square has its own ID. And now from here, let's say we're looking at this cell. From here, we just have to figure out where in the cell we are. And if we're, let's say, over here, then we add 0.5 to the y coordinate, or we subtract 0.5 from the y coordinate, and similar for the x and for the x as well. We can subtract it or add it. And that's how we can get individual IDs. So let's try to make that. Okay, so we have this ID over here. And let me zoom in a little bit. Over there. Yeah, okay, so what we actually need, well, there are two distinctions here, like, that we need to make. One is we need to know which side of this line we are on, like, and remember this uses symmetry, right? So we only really have to worry about one quadrant. And so we need to know which side of the line we are on to know if we're in this pentagon or if we're in that pentagon. And then later we figure out which side of the origin we were on to figure out if we were in this one or in this one or in this one or in this one. So first we need to figure out which side of that line we're on, and that's this slanted line. And so what we can do over here, we can say if d is larger than 0, well, then we're on one side of the line, otherwise we're on the other side of the line, right? And so here we could say id, well, let's try this, id.x plus equals, and we said, like, it's either plus or minus 1/2, right? And how do we know if it's plus or if it's minus? Well, that depends on where we are inside of the box, where we were originally inside of the box. Now, so whether the uv.x is negative or positive, right? So, or I can just say uv.x, the sign, give me the sign of that. So on the left side of the box, that sign is going to be -1. On the right side, it's going to be 1. So now this can be -1 or 1, but I only want to add or subtract 0.5. So I just do plus 0.5. And then similarly, if I'm on the other side of the line, then I need to do the same thing, but for the y. So plus equals the sine of uv.y times 0.5. All right, now in order to visualize this, I should probably quickly make a hashing function which takes a 2D, which takes the ID and turns it into a random number, so we can use that to make it brighter or less bright or whatever. I've written this many times, I'm just going to do it quickly. So this is a hashing function that takes 2 inputs and gives 1 output, that's why it's 21. And the 2 inputs is a vector 2. And then I'm just going to do some trickery here. First I'm going to multiply it by some larger number. And then I'm going to take the fractional component of that, so now it's somewhere between 0 and 1, and I'm going to add the dot product of p and p plus some other number, something like that, and then I'm going to return the fractional component of p dot x times p dot y. Now there are many different hashing functions out there. This is just one that I memorized and I use all the time, but feel free to plug in a different hashing function. So now let's see if we got something here. So we got this ID now, so let's see if we turn that ID into a color. So let me see here, float. So I'm gonna make a random value. I call it R, a random value for every pentagon. That's really what we want. So I'm going to do a hash 21 of ID, and now let's add that. So I'm going to do a call plus equals R, and then we get this, and it's all screwed up. Let me see. Let's turn this around, and it's still all screwed up. In that case, I need to check real quick what I did wrong. Right, of course. Yeah, I forgot that every other tile is turned around, right? So I have to take that into account because basically the X and the Y need to be swapped when it is turned around. And the easiest way that I found to do that is just use this checker here. So the checker goes between 0 and 1, right? So this is 0 or 1. That goes between 0 and 1. So what I can do here, because basically if that is 0, then I need to the sign to flip, or if it's 1, I need the sign to flip. And so what I can do for that, so this number is either positive or negative, right? If it's negative, then this evaluates to true. But I need to incorporate the checker in there. So if I multiply this by the checker, then that's not going to work because the check is 0 or 1. I need this check to go, I need this check to be negative or positive. So I can just subtract 0.5 from it. So now it's either negative or positive. And let's see what that does. And would you look at that? That fixed our issue for us. So now we have individual control over each individual pentagon. How cool is that? All right, so let's put this in its own function real quick. So let me just copy that from there to here. Go over there and then go over here and I say vec3 Cairo. So it's going to return a vector 3, and as an input it's going to take a UV coordinate and a K value, which is basically the angle of the slanted line. And it's going to return a vec3, namely it's going to return that ID plus the distance, right? So I'm going to return a vec3, which is the ID and then the distance. Let's see, so float K. So over here I have to take this out here. And that, I can take it out. All right. So now over here I can say vec3c equals Cairo of uv and mouse.y. Okay, and then over here I have to say c.z because the distance was in the z, and over here I have to say c.xy. Also over here I need to say c.z. I could just maybe multiply it. Okay, so that works. Although perhaps I should put the outline after everything so that it's on top. And then let's also animate this real quick. So instead of doing this, I'm going to multiply this by 1 plus the sign of this random number. And this random number is between 0 and 1, but I want to have the full range of the sign, so I have to multiply it by 283,185 by 2 pi. And then also let's add I time to it so that it kind of fluctuates. And yeah, I guess we could try this. All right, so now we have beautiful fading pentagons. All right, so I think I'm going to stop here. Yeah, Cairo tiles are really, really cool. I've been playing around with them for a while. There's a lot more to say about this. So I think I'll do another video about this in the future. But yeah, I encourage you to make this and use it in your project and let me know about it, because we need more Cairo tiling in the world, I think. Yeah, so anyways, thank you very much for watching, and I hope to see you next time.